Hi, you are watching a recorded lecture for the Coastal Ocean Environment Summer School in Nigeria. Today's talk is Introduction to NASA Physical Oceanography Distributed Active Archive Center, so-called PODAAC. I am the presenter, Jinbo Wang. I'm the PODAAC's project scientist. We are part of Jet Propulsion Laboratory, Caltech, located at Pasadena, California. The PODAAC is one of the 12 DACs under the NASA Earth Observing System Data and Information System, called Earthdata, managed by the Earth Science Data and Information System Project. The PODAAC is operated by JPL in Pasadena, California. Our mission is to preserve NASA's ocean and climate data and make these universally accessible and meaningful. We support big NASA satellite missions, as well as PI-led in situ and airborne campaigns. In addition to providing access to its data holdings, PODAAC acts as a gateway to the data stored at other ocean and climate archives. The data and various tools and services, ranging from visualization, discovery, and access, enable PODAAC to support a wide user community working in areas such as ocean and climate research, applied science and industry, natural resource management, policy making, and general public consumption. Our data will be always free. PODAAC is historically traced back to short-lived operation of the NASA CSAT mission launched in 1978. The CSAT altimeter, one of the several instruments on the CSAT platform, was among the first space-based remote sensing instruments dedicated to large-scale oceanography, but only survived for a few months. However, the measurements from this and other instruments represented scientific breakthroughs for the period and made demands for data storage, access, and distribution. Back in 1980, the Pilot Ocean Data System, so-called PODS, a distant processor to PODAAC, was funded at JPL to meet these demands, including implementing data distribution and subsetting. At that time, for local users, they can always access hard disks within JPL, but for the majority of the remote users, the data distribution relied on mailing time series plots and magnetic tapes. Later, to meet the needs of more emerging oceanographic missions, and the data infrastructure and management matured, a PODS morphed into NASA Ocean Data System called NOS. CD-ROMs were also used to replace magnetic tapes for remote data distribution. Finally, in 1991, the PODAAC was established as the archive of record and a distribution source for the successful Topex Poseidon altimeter launched in 1992. The altimeter has served as the foundation of the modern satellite observed sea level record. And during this period, the PODAAC developed improved infrastructure for data distribution and other online services as part of the family of DACs within the NASA Earthdata program. This included developing and deploying web services for data extraction, subsetting and visualization, data discovery and search, and metadata services. Now fast forward to 2019, when PODAAC was planning to support the future surface water and ocean topography mission, the SWOT mission, we realized that the on-premise data management and distribution becomes less practical. SWOT will generate more than 20 terabyte per day data flow, so a new strategy and data management were adopted to focus on leveraging the extendable scale and flexibility of cloud storage and computing. This was not only a PODAAC decision, but the entire NASA Earth Science Data Systems program has made a technical and business decision to move its data to the cloud to streamline the data management using open source software. The cloud-based system will also improve management of distribution and storage costs, promote open science, analysis in place, and interdisciplinary science across the spectrum of its measurements. It will also reduce the data movement. You don't have to download the data all the time. So by today, we have more than 1 petabyte of data hosted on AWS cloud from PODAAC alone. You can easily access and download this data from the Jupyter Hub account provided by the summer school. Over the past 3 decades, our data products have also expanded from altimetry to other oceanography variables, as well as other fields, including cryosphere and terrestrial hydrosphere. The new measurements included, for example, gravity from GRIS for global water cycle studies, ocean salinity, ocean temperature, ocean winds, and future surface waters from SWOT. Please visit our website, podaac.jpl.nasa.gov, for more information. By now, we are supporting more than 20 NASA missions. We have more than 600 data products. The data volume is more than 1 petabyte now. We publish more than 50 new datasets a year. All of these data are free and on your fingertips. As we mentioned earlier, in addition to NASA satellite missions, we also have a big collection of in situ and airborne data from NASA-supported field campaigns such as SPURS 1 and SPURS 2 for salinity, Ocean Melting Greenland OMG project, Sail Drone, Submesoscale Ocean Dynamic Experiment, S-Mode, and SWOT Pre-Launch Field Campaign Experiment. Recently, we also added data simulation products by the ECHO project. We'll talk about ECHO later. Next, I would like to highlight several data products hosted by PODAAC as an example to show you the collections we have, also show you how to search and access the data through PODAAC web services. The first project I want to highlight is the ECHO project. ECHO means Estimating the Circulation and the Climate of the Ocean. It is a NASA-supported project focusing on data synthesis through data simulation. It integrates diverse data sets into a single dynamically and kinematically consistent framework based on MIT GCM. It has been supporting NASA missions and contributing to future mission development. I believe there are other lectures in this summer school that will cover more details of ECHO. The 4 ECHO products have more than 3 terabytes of data, all of them now available on PODAAC. The second mission I would like to highlight is the Future Surface Water and Ocean Topography mission, the SWOT mission, as we talked earlier. It is a pathfinder mission using the Advanced Ke-band Radar Interferometer. It will be launched later this year and will provide wide swath ocean topography and terrestrial water measurements. The horizontal resolution for level 2 products are 2 kilometers for the ocean and 250 meters for the terrestrial waters. Again, it will produce more than 20 terabytes per day of data. The data will go directly to NASA Earthdata Cloud, which is hosted by Amazon Web Service. So the cloud-native programs are preferred for global SWOT data analysis because of the data volume. Here is a 3-minute clip produced by the SWOT mission showing you what SWOT is about.
So for me, SWOT is water.
SWOT is precision.
In one word, I would describe SWOT as beautiful.
SWOT stands for Surface, Water, and Ocean Topography.
SWOT will be observing the elevation of water surface in the ocean, on the land. The water surface height will allow us to assess the water storage in lakes and stream flow of rivers.
Our water is one of our precious resources. SWOT is unique because it is the first global view of our ever-changing water supply on Earth.
SWOT's main instrument is called COESSIN, which is the Ke-band Radar Interferometer. COESSIN is what sets apart SWOT from other missions. It's a unique instrument that we're flying for the first time.
The COESSIN instrument uses the 2 antennas, which are spread out on either side of the spacecraft, in order to bounce signals off of both of those to get a much larger view of the surface.
And being able to do it in very high resolution, higher accuracy, and also a wide swath so that we're able to measure large tracts over the Earth in a relatively small amount of time.
SWOT is a pathfinder mission using new technology to address transformative questions on climate change and its impact on our environment.
We're collaborating with CNES, the French space agency, for these programs, but we're also helping the global community to be able to contribute and collaborate towards making our home planet a better place.
SWOT will make our models better, and our understanding the water budget helps us be able to steward that precious resource.
If water is out of balance, we could face droughts, and it could also lead to floods.
SWOT is going to be observing water in oceans, and ocean science is essential for understanding sea level rise and climate change.
Now we are facing a time that we need to be very precise. Therefore, we can accurately predict what will happen in our coastal cities 50 years from now.
Understanding that it is a finite source and we can't rely on that forever is something that's really important.
I'm just so excited and can't wait to see how it impacts the lives of others.
Without really understanding the Earth, we cannot protect it, because we know that the missions that we work on are going to have an impact on our children and our grandchildren.
That was a wonderful summary of the SWOT mission. Now, the SWOT mission will launch in November of this year. For that reason, we do not have a SWOT data yet, but there are simulated SWOT data products produced by the mission and hosted on PODAAC right now. This shows you a screenshot of the 3 simulated SWOT data product of the sea surface height. Later, I will show you how to use PODAAC web services to search and download those data. The third project I would like to highlight is the Echo Simulation 1/48 degree. It is often called LSE 4320. The model has about 1 kilometer horizontal resolution at these latitudes in the Southern Ocean near Kerguelen Plateau. With this resolution, it can resolve ocean features with the horizontal scale down to order of tens of kilometers. We can see that the ocean is full of small-scale eddies that otherwise do not exist in low-resolution models or low-resolution satellite products. This particular animation shows the surface relative vorticity fields. These small-scale features will be potentially resolved by the SWOT mission. The global LSE 4320 has total about 2 petabytes of data. PODAAC does not have everything, but we do have a 15 regional subset. In this screenshot, I showed 3, but later on I will show you how to use PODAAC web services to search this dataset and download. In addition to data hosting, we often create animations to visualize the information content of a particular data product. This is an example showing you 3-dimensional temperature evolution based on one of the LSE 4320 regional subsets in the Southern Ocean. This subset is in a 300 kilometer by 450 kilometer domain of the 4 water column, but only the upper 2,000 meters is shown here. Because this is in the Southern Ocean, we often see the deep mixed layer shown in the vertical section. The filaments from the small-scale eddies can actually reach below the mixed layer, sometimes down to 1,500 meters. Because the LSE 4320 also saves hourly output, the fast evolving internal gravity waves are often visible here. By looking at this animation, we will be able to establish and enhance our intuition about the 3-dimensional ocean physics and dynamics, which will help us speed up our research analysis down the road. So this is just one example of many PODAAC animations that can be found on our website or YouTube channel. Just go to YouTube and search PODAAC. You will find a full list of animations that were produced in the past. Next, I will show you 3 core functionalities of PODAAC web services, which are data visualization, discovery, and access. Data visualization is done by our State of the Ocean visualization tool, which can be accessed through this link, podac-tools.jpl.nasa.gov/SOTO. If we click this link and go to the website, now we are in the PODAAC SOTO default view. It is preloaded with the global sea surface temperature product at 1 kilometer resolution. It is produced by GRIST, a measures Muir project in collaboration with PODAAC. There are a lot of things you can do on this website to visualize the PODAAC data product. I will not go through every functionality, but just to highlight several. We have a base map here, is a global blue marble. You can add additional coastlines and borders and rules by clicking this button, and also place labels. Let's take a look for the summer school location. Okay, this is zoomed in version. Now in this region, we do not have a huge temperature range because we are zooming into equatorial region. So we can do is to shrink the color range to emphasize the local temperature gradient by clicking this square palette. And now you can see the sharp SST gradient. Okay, this is just one functionality. Additionally, you can add more layers of different data product that hosted by PODAAC. This is Oscar, for example, ocean surface current speed, and also the surface wind speed from Cygnus, from ASCAT, sea ice coverage, ocean surface height, sea surface salinity. Yeah, just explore and look at your favorite data set there. You can do also do a data preview by clicking this button. Now, whenever you move your mouse, you can preview the data value in the bottom right box. Okay. You can also produce animations by specifying a range and download the GIF animation produced by SOTO. You can click this information button, for example, to preview the detailed description of this data product and use for links to more details. It also lists the data processing steps. Alright, this is just a simple introduction. Please try, let me know what you think. Another very important PODAAC service is data discovery. You want to find the most suitable data set for your research, for your application. How can you do it? The most straightforward way is to go to PODAAC website and search through different parameters there. If we click the link here and go to PODAAC website, this is the Find Data web page from PODAAC website. You can always go to this web page by clicking Find Data tab. Right now we have 772 datasets hosted here. Actually, some of them are duplications because we are in the process of moving data into the cloud. You can narrow down the data listing by different science disciplines, measurements, and missions. For example, if I am interested in the ocean heat budget, if I click this button, we have 29 matching datasets. You can use the filter on the left-hand side panel to continue to narrow down the search. I am interested in, say, echo product. Let's do long wave radiation. We have 4 matching datasets. We can go through each one of them, look into the details. This one is daily mean at half degree resolution from V4R4. And this one is monthly mean at half degree resolution. Okay, if we clear the filter, we go back to 772 matching dataset. Another way to do the search is through the advanced search box or through the search box here. They will give you the same search result. Okay, the second search I'm gonna do is through the search text box. I'm gonna search the simulated SWOT level 2 that we discussed earlier. The returning result is 8 matching data set. This is what we wanted because we have exactly 8 data set. The third search I'm going to do is the pre-SWOT level 4 through this search box. We have a 15 matching data set. Each of them is a subset of LSA 4320. All of them are cloud enabled. If we click on them, we are entering the landing page. In the landing page, there are detailed metadata associated with this dataset. The description talk about in general what this dataset about, and coverage and data access, documentation. Documentation is always important for us. Okay, there are also a lot of other resources, so you can explore the PODAAC webpage. And finally, data access. After you find your data, how do you download it? This is a very important step. There are many ways you can download data from PODAAC listed here, but I just want to promote one single tool called a Data Subscriber in this talk. It is an open source software hosted under GitHub PODAAC account. If we click this link, this is the GitHub page for PODAAC Data Subscriber. This tool is very easy to install and use. You can download PODAAC data just using one single line. This web page is very detailed but short. After you read through all the instructions, you should be able to start to use it no problem. There is a detailed installation instruction. Just use one line after you install Conda environment, and use this tool also is one line. There are 2 simple steps to set it up. First, get Earthdata login through this link. The second step is set up your Earthdata login. After that, you can just use this tool to download the PODAAC data. I do not expect a lot of trouble, but if you run into questions, please reach out to me through Slack. Okay, I would like to conclude my lecture by 2 points. The first one is that NASA Earthdata Cloud enables cross-continent collaborations without moving the data. This is an important point because NASA has been collecting huge amount of data that cannot be easily moved across continents. The only way of opening this big data to global communities is through moving code to the data through cloud platform, not moving data to your code through traditional downloading mechanism. This moving code to data mechanism will be well demonstrated in this summer school by using 2I2C's Jupyter Hub environment. It is unfortunate that this hub uses Google Cloud, not Amazon Cloud. But still, transferring the data between Google Cloud and AWS, Amazon Cloud, is much faster than transferring data between US and Nigeria. I would encourage the community in this summer school to establish long-term cloud-based research and educational collaboration. Second, PODAAC has a rich set of oceanography data free of charge. Please consider use PODAAC data for your research, application, and your classroom. We would love to hear your feedback. You can always send us an email to podac@podac.jpl.nasa.gov. Thank you very much for your attention. Hope you have a wonderful summer school.